Assalamualaikum and good morning. My name is Muhammad Afiq Iqbal and my other friend Yong Chongke, Christopher, Muhammad Firdaus. We are from Group 8. We are going to present about Pulse Amplitude Modulation or PAM. What is the Pulse Amplitude Modulation, or we call it as a PAM? Pulse Amplitude Modulation or PAM is a type of pulse modulation where the amplitude of each pulse is directly proportional to the amplitude of the input analog signal at sampling instant. PAM convert a continuous system analog signal into a series of pulse. Only the amplitude of the pulse changes. The width and the position remain constant. PAM is one of the simplest form of pulse modulation and is the foundation of more complex systems like PCM, PWM, and PPM. How does the PAM work? First, sampling the analog signal. The analog signal is sampled at regular interval. Sampling must follow the Nyquist theorem, which is Fs greater or equal to time Fmax to avoid aliasing. Second, generating pulses. A pulse equates for each sample. The time spacing between pulses is fixed, Ts. Third one is amplitude modulation of pulses. Each pulse's high amplitude represents the value of original analog signal at that moment. The higher the signal value, the taller the pulse. The lower the signal value, the shorter the pulse. Okay, the fourth one is transmission through channel. These pulses are transmitted through a communication medium, more susceptible to noise compared to PCM because noise directly affects pulse amplitude. Okay, now let's see the advantages and the disadvantages. The advantages is it is simple to generate and easy to understand and implement. The disadvantages is highly sensitive to noise, requires filtering at the receiver, and the last one, not suitable for long distance transmission without further encoding.
Hi, my name is Firdaus, and I will explain about types of PAM and misconceptions about PAM. So here are the three main types of pulse amplitude modulation or PAM. So the first one is ideal sampling. In ideal sampling, the pulse are extremely thin pulse, and we take the value of the signal at one instance. This is the most accurate type, but it cannot be done in real life perfectly. Then we go to the natural sampling. So in this method, the top of each pulse follow the reshape of the input signal. Because of the pulse lasts for some time, the value can change during the pulse, so this method is slightly less accurate. And then lastly, we go to the flat top sampling. Takes the signal value and holds it flat for a short time, making the pulse easier to read and more accurate for communication system. That's why flat top sampling is the most commonly used in practical of PAM system.
Hello everyone, I'm Christopher, and now I'll be walking you through the pulse amplitude modulation PAM from generation to demodulation. First, let's look at how we generate a PAM signal. We start with our original signal, like a voice waveform, which is this MT. Then we sample it. That means we take quick snapshots of each height every few moments. After that, we hold each sample, we stretch it out into a flat pulse, which is this ST. The result is a series of flat top pulses whose height match the original signal's height at each moment. And that is our PAM signal, which is ready to send. But how do we actually turn a smooth wave into flat pulses? And then we use a sample and hold circuit. Inside, there are two switches and a capacitor, which is like a tiny rechargeable battery. When it's time to sample, the first switch, which is a sampling switch, closes and the capacitor quickly charges up to match the signal's voltage. And then the switch is open and the capacitor holds the voltage steadily. Later, the second switch, which is discharging switch, closes to discharge the capacitor back to zero, so it's ready for the next sample. This cycle repeats over and over, charge, hold, and discharge, creating our train of flat pulses. So for the demodulation part, so how do we get the original signal back at the receiver? We use two simple stages. First, a holding circuit, and then a low-pass filter, which is LPF. Inside the holding circuit is a switch and capacitor. Think of the capacitor as a tiny rechargeable battery. So here's how it works step by step. So when a PAM pulse arrives, the switch closes and the capacitor charges up to match the pulse height. Then the switch opens and the capacitor holds the voltage until the next pulse arrives. This process creates a staircase-like waveform, which is a rough, blocky version of the original smooth signal, like the pulses here. So now, this staircase shape isn't perfect as it introduces what we call distortion because the signal is held flat between the samples. To fix this, we pass the staircase signal through a low-pass filter, or LPF in short. You can think of the low-pass filter like a smoothing tool. It rounds off the sharp edges, and removes the unwanted high-frequency steps. So the result is a clean, smooth signal that's very close to the original signal MT we started with it.
Hi everyone, I'm Yong Chong K. Now I'm going to continue the presentation with the application of the PAM. Firstly is the Ethernet PAM5 and PAM16. Modern wire networks use PAM to transmit multiple bits per symbol, increasing data rates. Secondly is the high-speed PAM4 links. It used in data centers, 5G backer, and optical communication to send more data without using extra bandwidth. Lastly is the optical communication. PAM helps convert electrical signals into light house with amplitude representing the data, allowing fast internet and fiber optic networks. Here are the diagram for the application. Now let's move to the recent advancement of PAM. PAM4 is one of the recent advancement. Traditional PAM uses two levels, 0 and 1 is like binary. PAM4 uses 4 amplitude levels, each pulse carries 2 bits per symbol. This increases data without doubling the bandwidth. Now I'll move to the application of PAM4. High-speed Ethernet. 400G Ethernet uses PAM4 to achieve faster data rates. PCLE 6.0. This is the latest version of connection in the computer. It connects the CPU, GPU, and also the RAM and Wi-Fi with other hardware. It allows faster transfer of data between the components. 5G communication. Backer links use PAM4 to handle massive data traffic. Data centers. PAM reduce the number of physical connections while maintaining high-speed communication. Now let's talk about the benefits of advanced PAM. Higher data rates. It transmits more bits per pulse, allow faster communication. Energy efficiency. It uses less power consumed per transmitted bit. Cost efficiency. Fewer physical links needed, allow lower infrastructure costs. Now I will talk about the benefits to social impact. Faster internet. It supports high definition streaming, video calls, and cloud services. It enabling AI and big data. High-speed links allow faster data processing for AI application. Environmental benefits. It reduces energy consumption and improve greener communication networks.
The last part, we go to the misconceptions about PAM. So in context of health, PAM signals can harm human health. That's not true because PAM is just an electrical signal that not contain any of radiation like X-rays or radioactive wave. And then listening to audio transmit via PM can damage hearing. That's not true because any audio can damage hearing if we raise the volume too high, not because of PAM. Now we go to the safety. PAM systems are dangerous because they are operated with high power. And then PAM signal can cause equipment to explode or overheat. That's not correct because any only power circuit design cause overheating, not on the PM technique itself. Now for the legal misconceptions, using PM automatically violates communication laws, and then PM is banned from public communication system. That's not correct because many systems like LEDs or some digital signal use PM legally. And then lastly for the environmental. So PM signal pollutes the environment. That's not correct because electric signal does not cause any physical pollution. And then last one, PM device damage wildlife or ecosystem. That's not correct because normal communication system frequencies have minimal environmental impact. I think that's all from our group. Thank you.